Hey everybody, this is our next lecture. Now this is chapter 16 in the old book, but it'll be chapters 21 and 22 in the new book, the one that you have access to. Chapter 21 is Conjugated Systems 1, Stability and Addition Reactions, and chapter 22 is Conjugated Systems Conjugated Systems 2, Pericyclic Reactions. So an introduction into, I guess, this unit of two chapters here from our book would be here. Did you ever wonder how bleach removes stains that are not easily removed with regular detergents? Most bleaching agents do not actually remove stains, but instead they react with the colored compounds in the stain to produce colorless compounds. The stain is still there, but it has been rendered invisible. When illuminated with ultraviolet light, the invisible stain can be seen once again. In this chapter, we will learn about the structural features that cause organic compounds to absorb visible light. Specifically, we will see that color is a consequence of special conjugated pi systems. In this chapter, or the two of them together from your book, we will learn about the structure, properties, and reactions of conjugated pi systems. You can see in the picture they have the before and after, this shirt with what looks like either paint or muddy stains, and then the after is the clean t-shirt. We're going to see how that works. All right, some things to review. Again, the sections aren't going to match up. You can find them yourself. That's good investigative work for you. But go back and study molecular orbital theory and pi bonds, conformations, enthalpy, entropy, Gibbs free energy, equilibria, kinetics, and energy diagrams. I would add on to their resonance, because we're going to see resonance in this chapter, or these two chapters. I know the outline here won't match what we have in our book, but we have dienes, conjugated dienes, molecular orbital theory, electrophilic addition, thermodynamic control, and kinetic control, things we've discussed in the past. An introduction to pericyclic reactions, the Diels-Alder reactions. I would say below that line will be the second chapter in your book, chapter 22. But then we have molecular orbital description of cycloadditions, electrocyclic reactions, sigmatropic rearrangements, UV-vis spectroscopy, color, and the chemistry of vision. And we have learned something about vision already, and at least in how our eye works to recognize colors, but we'll learn more here. All right, so we have 16.1 here, classes of dienes. There's accumulated dienes, ones where there are two double bonds right next to each other. There's conjugated conjugated dienes, in which you have a single bond between two double bonds, and then you have isolated dienes, ones that have multiple single bonds in between, or in other words, not single bonds necessarily, but there are sigma bonds in between. Now you can see also, if we look at the orbitals in accumulated dienes, maybe this picture is poor, but the middle carbon is sp hybridized, while the other two involved in the double bonds are sp2 hybridized. And so, again, the middle one is sp, then you have sp2 and sp2. If we were drawing an sp2 hybridized an sp hybridized carbon, we would have one p orbital above it, then we'd have one in front and in the back. If we looked at it from the side, if we looked at from this angle, that's an eyeball. We would have the carbon here again with the p orbital above it, and then the other double bond Actually, if I'm looking at, yeah, it would be to the left here, would look like that. There's your p orbital, your other p orbital. Okay, so when you look at this, the p orbital here and the p orbital there are perpendicular to each other, just like we see here and sort of there. All right, and then the other sp2 on hybridized carbon on the right will align itself to be parallel to this, so you get one pi bond here, and the other one on the left, the other carbon on the left is sp2 hybridized and parallel to the p orbital there, creating that pi bond. And so those two pi bonds are going to be perpendicular to each other. Whereas when you look at the conjugated system, the p orbitals are all parallel to each other, so they overlap. That's going to have a profound impact on the stability of conjugated systems. You see, with the isolated, we get a pi bond here and a pi bond there, but the carbon here creates too much of a gap in between for there to be an overlap between all four of those all four of those p orbitals. So there is no quote-unquote conjugation there. So this is from your book. Molecules are said to be conjugated when they contain a series of alternating single and multiple bonds that result in 3 or more consecutive atoms containing p orbitals. These neighboring p orbitals, overlapping via resonance, delocalize electrons throughout the system. This delocalization results in enhanced stability and altered reactivity patterns. The more we delocalize electrons, whether it's neutral molecules or negatively charged molecules, the better. And I've been saying that for the 2 semesters. If we spread out charge over a larger atom or many more atoms, it's always going to stabilize something. And so we see this conjugated system here with 3 double bonds creates a pi framework that looks like that. Right, we have 1, 2, 3, 4, 5, 6 atoms. And there's 1, 2, 3, 4, 5, 6 p orbitals that are all going to overlap, essentially creating one super strong bond between those 6 atoms, and they're all going to be, one super strong pi bond in a sense. We'll get to the specific details later, but this is just one of the situations. In reality, we've got 6 orbitals shown. There's going to be 6 different types of molecular orbitals. These are just from the atoms, so these are atomic orbitals. So 6 atomic orbitals creates 6 molecular orbitals. Here we have just 2 double bonds conjugated, and you can see that those 4 atoms are now connected through conjugation. So these would have 4 molecular orbitals. Over here we have an oxygen in the middle, and you see that it has a lone pair on the oxygen. Now, if we were to look at this oxygen, you'd say this is sp3 hybridized, because there's electrons coming off in 1, 2, 3, in 4 different directions. There's no double bonds, no triple bonds, so you would say it's sp3 hybridized. Well, here's the trick. The reality is that it'll assume sp2 hybridization in order to stabilize the molecule, if it can. So as we see here, this is now sp2 hybridized, so that's a p orbital. Let me put it right there, sp2 hybridized oxygen. If we were drawing this out, the oxygen being sp2 hybridized would have this p orbital, but then it would have an sp2, and there's going to be 3 of those, right? There's going to be another sp2 here, and finally an sp2 over there. And remember, for the hybridized orbitals, they always have the big lobe and the small lobe, but we ignore the small lobe in the drawings. So let me clear up something. This is the oxygen in there. And we have a carbon right here. So that carbon could be this, and it's also sp2 hybridized. So let's make this a P. Now you get a pi bond. This will also be an sp2, and so you're getting a sigma bond, and we don't have to really worry about the rest. On the other side, though, we do have a lone pair in the p orbital. So there are electrons in there. But what's not shown is the second lone pair. There's two of them. So we'll put a lone pair in the green one. Doesn't really matter. But then we have another carbon over here that's also going to be sp2 hybridized. And that's going to create this p orbital. That will overlap with this one to create a pi bond. And then you still have, and I'm sorry about the length of it, but made it a little too far away. You still have this sp2 orbital here, creating that sigma bond. And then the rest of the molecule. So you now have a lone pair in an sp2 orbital, whereas again, if we looked at it, you might predict that the oxygen would be sp3 hybridized. If it was sp3 hybridized, just as a refresher here, you'll have that as an sp3 hybridized orbital. You'll have that as a, let me get that out of the way. That as an sp3 hybridized orbital. That sp3, and finally that sp3. And you could get a lone pair here, a lone pair there. You've got your other carbon, which we saw was sp2 hybridized. So this one's sp2. And you still get a sigma bond there. And the other carbon with its p, and that one's sp2. And so you're getting a sigma bond. So we're actually increasing the strength of everything because we now have a pi bond between the oxygen and both of those carbons that didn't exist before. Doesn't look much different because we still have a lone pair here and a lone pair there. But technically the structures are different enough that this is better and this is worse. Over here we have a molecule that has a carbocation that is separated from the double bond by a single bond. And it turns out that that is also a conjugated carbocation. We could draw a resonance form like this, where, actually, let me delete that off. We have that resonance form. Which would be this, and this goes from secondary and allylic to tertiary and diallylic at that position, because we could have that go back or we could have that go back. If we look at the one on the left, we now have tertiary and allylic, which is just as good as the first one. So these are all valid, reasonable resonance structures for that molecule. So the carbocation is resonance stabilized. Now, this carbon has one hydrogen on it. So it should look like that. That means electrons are coming off in 1, 2, 3 directions. So, oops, not 3. This is an sp2 hybridized atom. So it has a p orbital, and the carbocation resides in it. And you can see that this pi bond is there. This pi bond is here, plus the p orbital from that carbon is there. So you get them all in conjugation. Again, we can spread out these electrons now over 5 atoms. This is better than either the 2, like these 2 for that pi bond and these 2 for that pi bond, from 2 to 5, or at least from 4 to 5. All right, so here are heteroatoms being involved in conjugation. Remember that conjugated double bonds have a sigma bond in between 2 double bonds. So obviously, not that I should need to, but the blue highlighted ones are the double bonds, and I'll highlight the single or sigma bonds in red. Now, this is actually a good practice because you'll see that on the right side, these are not going to be conjugated because the blue double bond over here is not separated by another double bond with only one sigma bond. This one over here is an isolated pi bond. I'll just call it a pi bond. I just noticed that I missed a bond, and so there's another sigma bond. And so you'll see that we have double, single, double, single, double, single, goes back to double. So we have conjugated double bonds all the way around that ring. We also have, let's change color here. We have double, single, single. So that double bond is not over here, is not conjugated to the nitrogen, but we have double, single, double there. So there is conjugation over here. On this molecule, obviously we have double, single, double, so those are conjugated to each other, and you see that for each of these we have a heteroatom, meaning something other than a carbon, oxygen or nitrogen being the heteroatoms here that are in conjugation with other double bonds. Ultimately, I could take the one on the right. Let me draw that again. All right. And we could take the benzene component of it and draw a resonance form like this. We make a copy of it. And I'm going to actually delete those, and so you'll see that because we have the resonance there, the double bonds end up here, here, and here. They're still conjugated, but now this pi bond is conjugated because there's double, single, and double. So the nitrogen is conjugated through here and through there to the benzene ring. But there's nothing we can do on the right because there's no, even if we have this double here, it's still single and single, or single and single before you get to that double. So there's nothing else we can do. It's still isolated in that resonance form. For each of the following compounds, identify whether each carbon-carbon pi system is cumulated, conjugated, or isolated. All right, so we look at this cis-aconitic acid, which plays a role in the citric acid cycle. We've got double bonds here, 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 and here. And we have single bonds that are shown in green, like that. The double bond here on the far left is isolated because there's single and single. The double bonds in the right side are actually going to be conjugated. The three of these together, because you have double, single, double, single, double. All right, on the next molecule, ocimene is present in essential oils of many plants. We've got single bonds I'm going to highlight here in gray and double bonds in red. Because we have single and single, this double bond is isolated. And then we've got double, single, double. So this system here, those are conjugated. For cis-jasmone, it's a constituent of many perfumes. Maybe it comes from jasmine. All right, we have, let's highlight the double bonds and single bonds. Let's do double bonds in blue, single bonds in red this time. All right, we've got a double, single, single, so this one is isolated. We've got double, single, double, so these are conjugated. And then finally in our carvone here, which is responsible for this flavor of spearmint, S-carvone, responsible for the flavor of caraway seeds or the odor of caraway seeds. We talked about that earlier. In the first semester, those are responsible for the flavor of rye bread, which is at least where I'm aware of it being mostly used for. You can see that these double bonds here are conjugated because we have double, single, double. And then over here on the left, this one is isolated. There's double, single, single, or double, single, single that way. Now, in a simple conjugated system like 1,3-butadiene right here, we have each atom being sp2 hybridized. And so we draw them like this, if you want. And typically we're showing like, hey, all four are lining up and we're getting that pi bond all the way across. But in reality, there's four molecular or four atomic orbitals. So there's going to be four molecular orbitals. And in other words, there's going to be four permutations of these atomic orbitals that give rise to the four different molecular orbitals. And you can see them in this picture. Either they're all in phase, or they're all out of phase, or they're somewhere in between. All right, so you have, when they're all in phase, the maximum overlap between the four orbitals, making this the most stable orbital. And you can see here's the molecular orbital. Looks like a big sandwich, maybe a hoagie or something, with the top and bottom buns, all with the positive overlap. The second one has bonding here, bonding there, but anti-bonding in the middle. So there's two bonding, one anti-bonding, for really a net of one bond. Whereas here we had three bonding. We go to the second one, and now we have 2 anti-bonding, 1 bonding, for a net of 1 anti-bonding. So you can see it's less stable than the one before it. Here's the bonding, right? Both are red, and then you have anti-bonding and anti-bonding. And up here we have 3 anti-bonding, which is obviously the worst. All right, so the second most stable molecular orbital has 1 node. Note the symmetry around the node. The third most stable molecular orbital has 2 nodes. Note the symmetry around the 2 nodes. Really, it's like symmetrical through the middle of the molecule there. And then finally, the least stable molecular orbital has 3 nodes. Essentially, there is no overlap in this molecular orbital, thus it is the least stable. We go from 0 nodes to 1 to 2 to 3. And going down here, reading from 5, there's 1 p electron for each of the 4 p orbitals in the pi system. Place 2 electrons in each molecular orbital, starting with the most stable until all 4 are used, right? We have 2, wait. This is a pi bond, there's a pi bond, that has 2 electrons, that has 2 electrons, for a total of 4 electrons, all right? So if we have, you'll see there's psi 1, psi 2, psi 3, psi 4. If there's only 4 electrons, they're going to go in psi 1 and psi 2. And this had the 3 bonding. This has 1 bonding overall. So for a total of 4 bonding. All right. If we were to take the atomic orbitals, the 4 atomic orbitals would be split like this. And so you're getting this to be more stable, much more stable, in fact, because they're here, the psi 1 and psi 2 are both less in energy than where we started off with E equals 0 there. So being below E equals 0, these are filled bonding orbitals. Being above E0, these are unfilled antibonding orbitals. And so, as we see, due to conjugation, 1,3-butadiene is more stable than if those 2 double bonds were isolated. So why is this not a viable representation of the psi 2 molecular orbitals of buta-1,3-diene? The answer is that it is not a viable molecular orbital because the system is not symmetrical. Certainly not around the node. The node is right there, and there's no symmetry. Right, one side of the node has 3 orbitals, the other side has 1. When doing these, you need to have symmetry. For 2, which of the following would you expect to be more stable, and why? Well, we have 1 and 2 nodes, and 1 node here. So I'm looking at that, and I would say this one would be more stable because it only has 1 node. Therefore, there's more overall overlap between the 6 orbitals on the right than there is on the left. There's only, like those, you get 3 atoms spread out there, 3 atoms there. So it's always going to be that the fewer nodes there are, the more stable it'll be. An increase in conjugation allows for more p orbitals to overlap, increasing the amount of delocalization possible in the pi system. With increased conjugation comes enhanced stability. Not enhanced abilities, sounded almost like a superhero thing there, but enhanced stability. So as we see with ethene, if we, let me get some straight lines here. For ethene, the psi 2 star, the antibonding one, there you see the buta-1,3-diene is a little bit higher for the LUMO for these. Hexa-1,3,5-triene is even higher than buta-1,3-diene. And the same could be said for the bonding orbitals. Right? That hexa 135 triene, its most stable orbital is lower in energy than the most stable one for buta 1,3 diene, which is more stable and lower in energy than the most stable one for ethene, the HOMO. All right, so these are what we're looking at. You'll notice that for each of these, all of the orbitals below E equals 0 are filled. So ultimately, hexa 135 triene has the enhanced stability relative to buta 1,3 diene and relative to ethene. All right, so we're going to go to the end of your chapter and learn about colors and vision again. All right, so most of the standard compounds you've worked with in the lab, like acetone, benzoic acid, diethyl ether, well, we could use benzaldehyde as well in there. They're colorless, which implies that these molecules do not absorb or reflect light that we can see. So it's not in the visible spectrum. So we've seen this picture before. Our vision ranges from about 380 nanometers to about 720 nanometers in wavelength. That'd be the violet and the deep reds. Molecules can also undergo electronic transitions. These electronic transitions are a result of electron excitation from occupied to unoccupied orbitals. For example, from the HOMO to the LUMO, the highest occupied molecular orbital, to the lowest unoccupied molecular orbital, as I've discussed many, many times so far. Because the HOMO is the last bonding orbital and the LUMO is the first antibonding orbital, this excitation is referred to as a pi to pi star transition. The difference between the HOMO and LUMO energy levels is termed the lambda max because it represents the wavelength of maximum absorption. Not the greatest wavelength that can absorb light, but the one with the greatest absorption, the one that absorbs it the most. That is the wavelength that corresponds to the exact energy of the pi to pi star transition. With increasing conjugation, the HOMO to LUMO energy gap decreases, causing the irradiation frequency to move into the ultraviolet and visible regions of the electromagnetic spectrum. So let's draw that out again. If we have from E0 to there, HOMO to LUMO. We actually didn't do this one before, but you can see that the gap between these is getting much, much smaller. Right, and let me try to emphasize it here. All right, and so on the leftmost one, we have ethene. You have a large gap there corresponding to 165 nanometers. That is going to be in the ultraviolet region. For buta 1,3 diene, the gap gives or correlates to an energy of 217 nanometers. That's also ultraviolet. For hexa 135 triene, 258 nanometers. That's also going to be ultraviolet. For what it's worth, UV light ranges from 100 to 380 or sometimes 400 nanometers. Okay. And you've probably heard of the UVA. Let me write this correctly. There's the UVA region, the UVB, and the UVC parts of the spectrum. The UVC is from 100 to 280 nanometers. The UVB is from 280 to 315 nanometers. And the UVA is from 315 to, I'll put 380 nanometers. Now this data is from the World Health Organization, as far as, their ability to monitor UV exposure, sunscreens, and things like that. You'll see UVA, UVB, UVC spectrum being blocked. You'd want something that blocks the whole spectrum because obviously. UV light is destructive towards us. And you can see ethene, buta-1,3-diene, and hexa-1,3,5-triene all absorb light in the UV spectrum. Ethene, because it's at 165, would absorb light in the UVC spectrum. Buta-1,3-diene at 217 nanometers is also UVC. And hexa-1,3,5-triene at 258, well, that's also UVC. But it's getting at 258 close to there. And then, so as we add more and more conjugated double bonds, that gap gets smaller and smaller and smaller and smaller, meaning, again, let me write the equations. Delta E equals H nu, or it's HC over lambda, where lambda is the wavelength. So if delta E is getting smaller, the wavelength is going to naturally go up because it's in the denominator. These are inversely proportional. So as you add more and more conjugated double bonds, the delta E gets smaller, so the wavelength goes up. We see 165 to 217 to 258. Now we look at this picture, and we've got buta-1,3-diene, we've got hexa-1,3,5-triene, then there'd be octa-1,3,5,7 tetraene at the far right, and you see that it's at 290 nanometers. That one will be in the UVB part of the spectrum where it absorbs light. With increasing conjugation, lambda max increases, moving farther into the UV region, really meaning closer to the visible region. For example, lycopene and beta-carotene are highly conjugated and therefore are colored molecules. You look at beta-carotene here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 conjugated double bonds. We could count the number of atoms here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 atoms involved in conjugation there for beta-carotene. So we get the color of carrots from beta-carotene because it is so highly conjugated. For lycopene, that one has, I don't see it in the picture here, but lycopene is a very similar structure, and that is responsible for the red color of like tomatoes. And that one also has 22 conjugated atoms together. We'll see that one on the next slide. But over here, we see in the table the lambda max for ethene, buta-1,3-diene, hexa-1,3,5-triene, octa-1,3,5,7 tetraene, deca-1,3,5,7,9 pentaene, dodeca-1,3,5,7,9,11 hexaene, and you can see we have the UVC, 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 UVB, UVA, and UVA for the dodeca-1,3,5,7,9,11 hexaene, getting close to, there we go, sorry, I made a typo, moving close into the visible region. 380 is the very limit of what humans have, but usually you'll see it listed as 400 nanometers. So either way, we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 double bonds conjugated together. The beta-carotene had 22, so really maybe anywhere in between there and further, you're getting colored molecules. We see here lycopene and beta-carotene. Again, the structures are pretty similar except for the ends of them. And you can count them, you see the same number of conjugated double bonds for each. Because of their extensive conjugation and small HOMO to LUMO gap, they absorb light in the visible region. Meaning if they absorb visible light, they're reflecting some of it. not all of the light is getting reflected off, and it's not passing through it either. They're not transparent like glasses. So, right, if it's absorbing, let's see, lycopene, lambda max of 472. We could look at this table. It's somewhere in between here. The color of light absorbed is going to be bluish green or blue, and so it's going to be a reddish orange color, right? The lower the wavelength, let me do this properly, 380 nanometers to 400 is the blue end, all the way over to 720 is the red end, and then you've got in the middle of that, give me a second here, you've got orange, yellow, green, blue, and we don't really actually see violet. Our brains kind of invented, but either way, and then indigo is also in there, but anywhere what we're looking at is the color of light absorbed, right? The ones with the least amount of conjugation are absorbing the highest energy light. So again, lycopene at 472, beta carotene at 450, they're absorbing in the bluish green region, so you're going to the opposite end towards the orangish and red colors, hence why they look orange or red, I guess. Which of the following molecules would you expect to absorb in the visible region of the electromagnetic spectrum? Well, certainly not that. Certainly not this. And certainly not that. Those have only like no double bonds, or only up to like 3 conjugated ones. If you look at the other two, we've got 2, 4, 6, 8, 10, 12, 14, 16, maybe that whole thing is conjugated. It's only 10 atoms though in total. And then, but you have over here, all the way over to there. So I would expect that to be conjugated enough to give us a color. And over here, you've got 6 atoms that are conjugated like this, all the way over to there. Now let's count them out. There's, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that looks like that should also work. When you took general chemistry, you should have used in the laboratories a UV vis spectrophotometer, ultraviolet invisible light, used to detect really the colors of things. We use that for colorimetry, and colorimetry is really used to determine the concentrations of solutions that generally have color, but it doesn't have to be, because it could be absorbing ultraviolet light as well. But anyways, the way these work, we have a light source that's going to irradiate, and that light's going to pass through a collimator, a lens essentially, to focus the light, because light bulbs irradiate in 3 dimensions in a sphere essentially, but we want it to go directly at our sample. The light then passes through a diffraction grating or a prism, and that'll split apart the colors. Into the rainbow there. The next step is a wavelength selector. And so the instrument will, as it's scanning the sample, essentially, it's going to use the wavelength selector to incrementally use from ultraviolet to the visible, blue in the violet region or blue, and then all the way to the red, and do it incrementally. You can also select, hey, this is one wavelength I want to use, only pick that wavelength. But if you do it in the normal way, you can get a whole spectrum that would look, let's say, like 100 nanometers all the way up to 900 nanometers Let's just say that. And then you might get a spectrum that looks something like that. We talked about NMR spectroscopy already. We talked about infrared spectroscopy. We're now in the UV vis. All right. Over here was IR, and those ones we did down, they went down. The UV vis is over here, and then we also had the NMRs over here in the radio waves, and those had, their peaks, whatever. So interesting, we can use all these different types of light to give us different information, right? NMR spectroscopy gave us the nuclei flipping, which allowed us to really figure out the structure of molecules, or at least if they have hydrogens or carbon-13 or whatever. Infrared spectroscopy gives us information about functional groups and how atoms stretch or rotate or wag and wiggle around each other. And then UV vis is just absorption of electrons going from HOMO to LUMO, which is pretty interesting. But anyways, that light then passes through your solution, and if the solution absorbs any of it, then you're going to get a change here in the detector, ultimately from what you started with. Again, it's a solution, so you have a solvent in there. So the first thing you would do in your UV vis is run a blank. So you might put just solvent. Let's say the solvent is water. You'd run this with water. Water does absorb visible light. It does, if you look at water from a distance, great bodies of water look blue because they're absorbing some red light. If you went back to the chart, if you're absorbing red light, let's say wavelength around 600 nanometers, it's orange-red light being absorbed. It'll look a bluish green or cyan color, which is what I would say blue or water looks like. It's very weak. A glass of water is clear and colorless because to the length of the sample, it's not enough for our eyes to notice the absorption. The longer the path length through the sample, the more light ultimately gets absorbed, and so you'll see more and more color. In this UV vis spectroscopy, the chromophore is the region of the molecule responsible for the absorption of the light, whether it's ultraviolet or visible, while the groups attached to the chromophore are going to be the oxochromes. So we see the oxochromes are there, while the chromophores will just be the part in the middle because they have the conjugated double bonds. And oxochromes will also be those green parts. The oxochromes are there, and they actually can have an impact on the value of lambda max. For example, alkyl groups will increase the lambda max by approximately 5 nanometers for each one. So these additional methyl and ethyl groups will increase the lambda max a little bit. And there's many other ways we could look at these with different types of structures, but it's not that big of a deal. But either way, when you look at molecules like lycopene and beta-carotene, they have the same number of conjugated double bonds, but there's the end caps, I'll call them, are different. So lycopene and beta-carotene, although they have the same amount of conjugation, one's orange and one's red because of the oxochromes are different. And again, you can see that here, the lycopene and the beta-carotene are nearly the same in this region to here, but we have the end caps being different. And so lycopene is going to be the red color, and the beta-carotene is going to be orange. In other words, you see lycopene absorbs a higher lambda max because there's this extra double bond that is not in conjugation, and they each have these methyl groups sticking off. And I should have highlighted, this over here for the beta carotene. But red just has a little bit more with that double bond, and arguably the extra methyl groups here and there, whereas beta carotene. Either way, they make a contribution to the color of those oxochromes. One of the rituals of doing outdoor activities in the summer is lathering every uncovered part of skin with sunscreen. The reason we put sunscreen on is ultimately to prevent sunburns and to prevent skin cancer. There's two kinds of ingredients used in most sunscreens. The first kind includes inorganic materials like titanium oxide and zinc oxide, which scatter light or reflect harmful rays away from the skin. They look white. Their colors are white, and white reflects all colors. That's why they look white. So the first thing is to get rid of all the visible stuff, and it's going to get rid of some and reflect some ultraviolet stuff. The second kind absorbs UV radiation, and you see examples down below of these organic molecules that absorb ultraviolet. There's some conjugation there, but not a lot, not enough to absorb visible light, so the sunscreen still looks white, but they're going to have enough to block or really absorb ultraviolet light, and so the electrons will go from the HOMO to LUMO, and then they'll relax back down to the HOMO and release that amount of energy in the form of heat, not ultraviolet light, because the gap ultimately is pretty small. So that's the benefit of those, although really all of these things are in question lately. I've certainly, with me having kids in the past year or so, we've been seeing you got to use mineral-based sunscreens, not stuff with organics. And so these are organics, and they're used in sunscreens. So who knows? This stuff's ever changing, as with everything in the world, what's safe and what's not. So we put the sunscreen on to, in part, prevent skin cancer. All right, skin cancer is caused by ultraviolet light, damaging DNA ultimately. Most of the ozone that is irradiating from the sun that reaches the earth is going to be absorbed by the ozone layer, converting it into oxygen, O2, and radical oxygen atoms, which then recombine to form more ozone, and they release that extra energy upon reacting back together to reform the ozone. They release that in the form of heat. So when we have things like the ozone layer hole, it allows more ultraviolet light to get through. Our ozone, even if it's fully intact, doesn't block all ultraviolet light. So there's always some getting to you, even here, not in the Antarctic, because that's where the ozone hole mostly is at this point. So there's two types of damaging ultraviolet light, the UVA and the UVB. UVB is higher in energy and more damaging, but UVA is also dangerous, all right, as it can penetrate the skin more deeply. The longer the wavelength, the more penetrating it is. It has been estimated that 1 in every 10 Americans will develop skin cancer. That means that there is a 10% chance that you will develop skin cancer at some point in your life unless you take precautions. The mechanism by which UV light damages DNA has been extensively studied, and many pathways are responsible. One such pathway involves a thymine base of DNA absorbing ultraviolet light to give an excited state that is capable of undergoing what's called a 2+2 cycloaddition with a neighboring thymine base. We'll learn about that in the next half of this chapter, but in this PowerPoint slide, but in chapter 22 of your book, you'll see the 2+2 cycloadditions. And so we can see here we have these two thymines, and they each have double bonds that are actually facing towards each other. Remember, with DNA, you've got adenine, thymine, guanine, and cytosine, and those are the base pairs, adenine, thymine, and guanine, and cytosine. that pair up in the double helix of DNA. This is just some general strand of DNA where you happen to have two thymines next to each other. If that's the case, and ultraviolet light comes in, that's the H nu there, a 2+2 cycloaddition can occur, creating this four-membered ring in between them. That's now damaged DNA, which can then get repaired, but sometimes the repair of DNA leads to errors, and those errors can lead to cancer. All right, so how does bleach whiten clothes? Well, it turns out bleach, which is sodium hypochlorite, NaOCl, will react with double bonds to create this. You have conjugated double bonds in every color on your clothing and in most things in our life. Things that are colorful, from paints, dyes, pigments, whatever, have these conjugated double bonds. You add a bleaching agent, and they're going to convert a double bond into a single bond due to some addition reaction. So the conjugation breaks from beginning to end up here, and now you have shorter strands that won't be long enough to absorb visible light. So yeah, they may absorb ultraviolet light still, but they will no longer absorb visible light. So if it's, let's say, something that you want to be white, and this is some stain, then now the stain is structurally different and invisible to visible light, so it would look white again. The stain is still going to be embedded and absorbed into your clothing and onto the clothing. You can't really get the things off all the time. I can tell you that from experience. So it's still there, but if you change its structure and it's no longer absorbing in the same areas of the color spectrum, then it can make your clothes look white. So you see here's a UV vis spectrum before bleaching. You have some absorption of ultraviolet and more visible, so it's going to look like a color. Then you add the bleaching agent in there, and now it's not absorbing anything visible because the conjugated double bonds are gone. So you only have UV. Now, if you've ever been under a black light, wearing a white t-shirt or something like that, you'll notice that white shirts glow. The reason white shirts glow under black lights, which are giving off ultraviolet light, is that they absorb in the ultraviolet spectrum, but when the electrons relax from LUMO to HOMO, they release or emit that extra energy in the visible spectrum, which will be right on the edge of the ultraviolet and end up being in the visible spectrums, the blue. That's why the white shirts glow bluish under black lights. So technically, we already talked about how vision works in our eyes, because we talked about the isomerization of a cis double bond to a trans double bond in the cones of your eye. We see here 11 cis retinal will attach to opsin at the amine of it, the nitrogen right there, and create rhodopsin, this enzyme with the 11 cis retinal attached, forming this imine here. And it was that when light comes in here, visible light, it's going to end up switching this cis double bond here to a trans double bond. So I'm going to just simplify this to R. You know what? Let me do it down here. R, then ultraviolet light or visible light comes in and converts this to the trans double bond over here. And the visible light causes that change. You now have a difference in how the electrons go because the cis is going to be higher in energy than the trans. And so therefore, ultimately electrons are going up in energy, then they're going to go down in energy, and that's going to cause an excitation in your optic nerve, creating a signal to your brain that it recognizes as a color. This was sort of proven with evidence with Koji Nakanishi's work at Columbia University, where he made this analog of 11-cis retinal that he attached to opsin in rats, and you see that the double bond in Nakanishi's analog is a cis only with a 7-membered ring. You can't have the double bond be trans. It has to be 8 or more. So this locked the cis conformation or cis configuration in opsin and to therefore the rhodopsin. And so when light would come in, nothing would happen and the rats remained blind. When rhodopsin is excited photochemically, a change in shape occurs that causes a release of calcium 2+ ions. The calcium 2+ ions block channels through which billions of sodium ions generally travel each second. The decrease of the sodium ion flow culminates in a nerve impulse to the brain. And so again, it's the cis to trans isomerization that has been proven to cause that. And it's really just due to conjugated double bonds. That's pretty neat. Here we have some methods for preparing conjugated dienes. We have, let's see, the name of this would be 3-bromo bute 1-ene. All right, and tert butoxide, potassium tert butoxide, which is a big bulky base. That big bulky base is going to take a hydrogen off of the terminal position, preferentially over the hydrogens right here. And so the other option is if the base were to take this off and create a double bond. If I number these carbons 1, 2, 3, and 4, we would have 1, 2, and with accumulated dienes, the dot represents the carbon connecting those atoms. And then let's do 4. We still would have a hydrogen because there is a hydrogen here. And then I'll put CH3. You have that. This double bond is like di-substituted, whereas this one right here is only mono-substituted. So you might think the cumulated diene would be better, and maybe it is. But specifically they're going to choose the tert butoxide there to prevent the formation of that cumulene and instead have the conjugated diene. So we could take the 3-bromo bute 1-ene, or we could take 2,3-dibromo butane. And again, potassium tert butoxide, you got hydrogens at these terminal positions. So one base will remove that bromine, another base molecule will remove the other bromine to make, in this case, they're both the same molecule. So this is 1,3-butadiene. Why is potassium tert butoxide used? I already mentioned that. It's to enforce the deprotonation or the elimination from the terminal position. You'll see that the bond length here this is a sigma bond, and this is a sigma bond. They differ between the conjugated system and in just regular ethane. And the reason is that the carbons in 1,3-butadiene, these are each sp2 hybridized, while the carbons in ethane are sp3 hybridized. And so because you have sp hybridized atoms, those orbitals are going to be shorter. If we were to look over here, let's say these are sp2, forming the sigma bond in there. All right, and I have the double bonds outside of that. In ethane, you've got, and I'll put a hydrogen up there, whatever. So these carbons are sp3, and you get your sigma bond there. So sp3, a little bit longer, meaning the bonds are going to be different here. So as I mentioned in the previous slide, it depends on the S character or the hybridization. You see that if you have the you can actually have p orbitals of two atoms lining up, like this is a p and another p could line up to form a sigma bond. Oops, I'll just do it this way. And that would be a pretty long bond because it has 0% S character. With sp3 hybrid orbitals, they're a little bit shorter at 25% S character. With sp2, they're 33% S character, so again, they're getting smaller. To sp is smaller, and then if there's like two hydrogen atoms, they're going to be really close together because they have 100% S character. Here we have relative stability comparing heats of hydrogenation. All right, so we have the but-1-ene going to butane, and we have 1,3-butadiene also going to butane. Now you'll see that there's two molecules of but-1-ene versus one molecule of 1,3-butadiene. We're adding, therefore, two molecules of hydrogen to the two molecules of but-1-ene and two molecules of hydrogen to the one molecule of 1,3-butadiene to make, ultimately, butane. So the difference here is that in but-1-ene, it releases 254 kilojoules per mole, while the 1,3-butadiene releases 239 kilojoules per mole. And so there's a difference of 15 kilojoules per mole for these reactions, meaning that the but-1-ene, being higher in energy, is actually less stable, and the 1,3-butadiene is more stable, again, by 15 kilojoules. All right, so excuse the poor quality of this image here. Again, I took this from the textbook you'll be using. I do like this model better than the previous one, which is from the other book, and the reason is that we can use the same number of molecules here to make a comparison. At the top, we have cyclohexa 1,4-diene. The two double bonds are isolated. You have the single bonds, two of them in between the two double bonds. And then you have cyclohexa 1,3-diene, which has double, single, double. So those are conjugated in there. And so I like that a lot better. You see, if we hydrogenate one double bond, in each of those we end up with cyclohexene. And in there, the cyclohexa 1,4-diene releases 120 kilojoules per mole in the first step, and then another 120 kilojoules per mole for the second step. So in total, there's a drop of 240 kilojoules per mole. If we go from cyclohexa 1,3-diene, well, it turns out that, well, we know that this process is losing 120 kilojoules per mole, but we see that the total change is 231 kilojoules per mole. So if we take the 240 minus the 120 from the second step of each, again, the first one should be, well, 120. If I take 231 minus the 120, we get 111 kilojoules per mole. So in this case, the difference here is going to be 9 kilojoules per mole, because you see 111 there, because it wasn't 120. So it's releasing 9 kilojoules per mole less energy released in the conjugated system. So in other words, as we can see in this graph, the conjugated system down at the bottom is 9 kilojoules per mole more stable than the isolated one, or roughly 2.2 kilocalories per mole. All right, so rank the following compounds in order of increasing stability. Right, we have the double bonds, I'll highlight in red, and then single bonds in blue. Just kind of connecting the double bonds together. So we have 3 in conjugation at the right. And so I'm just going to put 3 conjugated. Here we have this one being isolated, and these are 2 conjugated. And let me highlight over here too. All right. We have these 2 conjugated and this one isolated. And then we have isolated and isolated. That's one thing to look at. But then we have, like, clearly D is more stable than A, which is less stable. And in, like B and C are in the middle because they each have 2 conjugated double bonds and 1 isolated. So the next thing to look at is the types of double bonds. The isolated one here is disubstituted. We have trisubstituted. This one's tetrasubstituted. This one's di. This one's di. And this one is trisubstituted. So I think it's obvious that B is more stable than C because it has the tetra and tri-substituted. Right, the di-substituteds cancel tri, and then you have di versus tetra. So B is more stable than C, and so that would be the ranking of stability. All right, so this is actually in chapter 22 of your book, conformations of 1,3-butadiene. And you can see that there are the S-cis conformations and the S-trans conformations. And so when talking about stability of these, we'll see that actually the S-trans is more stable. Now, neither of the double bonds are trans or cis in either of these. They're both terminal alkenes, so they can't be cis or trans, but it is the single bond that's acting like we would have a double bond here that would be cis, or this one being trans. It's kind of the reverse. Instead of 2 singles and a double, we have 2 doubles and a single, and we can still get the same sort of conformations. And you can see in the molecular orbital pictures of them, whether they're cis or trans, the p orbitals that are unhybridized are still able to overlap. The difference in energy between the S-cis and S-trans is 12 kilojoules per mole, or again, roughly 3 kilocalories per mole. Okay, rank the 3 carbon-carbon bonds of 1-butene in terms of bond length from shortest to longest. Well, what we need to do is look at the hybridization of each of those atoms. And we have sp2 hybridized for those two and sp3 hybridized for those two. The sp2 is going to be the shortest, because we know that the sp3 will be the longest. sp2 is in the middle and sp is the shortest. We don't have any sp to worry about here, but since we have 2 sp2 orbitals coming together, they're forming the shortest bond. It's also the strongest bond. It's a sigma and a pi. So the stronger the bond, the shorter the bond. Then we have sp3. sp3 will be the longest. And finally, the sp2, sp3 will be intermediate. All right, frontier orbitals and frontier orbital theory is technically in chapter 22 of your book. Frontier orbitals are going to be considered the HOMO and LUMO orbitals. And the reactions we're going to see for these highly conjugated molecules will occur, as with all reactions, between the HOMO of one molecule and the LUMO of another. The nucleophile was always going to be the HOMO, while the electrophile was going to be using its LUMO. All right, but when we're talking about colors and stuff, you know, excitation went from HOMO to LUMO of the electrons, and then from LUMO back down as they relaxed. It's not much different here. So those are the frontier orbitals, and frontier orbital theory just states that the reactions, because that's what we're getting to here, between molecules occur between the frontier orbitals. Here we see excitation of an electron in the HOMO of a molecule to the LUMO of another molecule. This looks like it's 135 hexatriene. So the HOMO there to LUMO gap is in the UVC spectrum. Section 4 here of this book is electrophilic addition. And so we're going to take molecules that have double bonds, again, and react them. We saw this early in semester 1. We'd take an alkene and react it with HBr, and that would make a molecule like this, where we have Markovnikov addition. The bromine adds to the more substituted carbon of the double bond. When we take 1,3-butadiene or buta-1,3-diene and we react it with HBr, what do you think we're going to get there? Well, it's not as straightforward as you might expect. So let's see what happens. So we have buta-1,3-diene and we have HBr. If we ignore the double bond on the left, the first step in the hydrohalogenation was addition of hydrogen. And that would occur creating a carbocation either at the primary position or at the secondary position. And we discussed ad nauseum, I think, that the secondary is more stable than the primary. So we get that preference, and then the bromine that was kicked off would attack the secondary position to make this molecule here. And if I make this color-coded, we'll do it like that. The hydrogen would be here, and you get that as a product. But we do kind of want to consider the fact that there's an intermediate here. All right, you have this allylic, and it's a secondary carbocation. If the bromine were to add here, this is what we'd call a 1,2 addition. If, however, this undergoes resonance, where that double bond moves to there, we end up with a carbocation here. And yes, this is allylic, and it's only primary, so it's less stable. But we have a di-substituted double bond over here versus a mono-substituted double bond. All right. So it turns out if the bromine were to attack here, this would create what's called the 1,4 addition product. And so we would get that. And over here, in the 1,2 addition, we get this. It turns out that the 1,2 addition is going to be done under kinetic control, meaning it's going to be under cold conditions, like at 0 degrees Celsius. We get the 1,4 addition under thermodynamic control at, for example, 100 degrees Celsius. Again, we have a di-substituted alkene versus a monosubstituted alkene. Either way, the hydrogen added at that position, so this is the 1, 2, carbon 1, 2, 3, 4, and this is the 1,4 product right there. Under thermodynamic control, you get the 1,4 addition product. Under kinetic control or cold conditions, you get the kinetically controlled 1,2 addition. All right, so predict the products of the following reaction and propose a mechanism that explains the formation of each product, or maybe products. There's 2 alkenes here, though, and there's only one equivalent of HBr. So let's draw this out. All right, we could have that double bond attack, or we could have that double bond attack. And so we could put, I'm going to put the hydrogen at either of the locations for each of these reactions. We could have the hydrogen add here, or it could add there, resulting in a resulting in a carbocation there versus here. At the other one, we could add the hydrogen here or there, resulting in the carbocations here or here. We'll label those as tertiary and allylic. This one is secondary, and it's only secondary. All right, but maybe that one does a hydride shift. Actually, just like that. Resulting in that, which is the same as the other one we saw. Let me put here. All right, so either way, for the top reaction, we're left with this tertiary allylic position. And now we've got a bromine to add in there. And I'm sorry, this hydrogen should be blue technically to be consistent. All right, so now we have the bromine. The bromine, or the bromide, would add there and create a product that looks like this. All right, so yeah, we had tertiary allylic, and then we have a di-substituted alkene product right there. If the bromide were to attack here, it's just secondary, and we still have the di-substituted, so that doesn't benefit us in any way. It's not conjugated, so that also doesn't help. So what if instead we had the resonance form from right there? Now this is secondary allylic, and the bromide could add in right there, creating a product that would look like this. And now we've got from here a tri-substituted double bond. So we would get this under kinetic control and this under thermodynamic control because it's more stable. It does say, I guess we might have a mixture. It doesn't specify if it's under thermodynamic or kinetic. Those are the two possible ones there for the top reaction. In the bottom reaction, this one is secondary, and that's it. This one is secondary allylic. If we did a alkyl shift, a methyl shift, that would create this, and that's not good. So don't do an alkyl shift. Wait, I'm sure you couldn't see because whatever. You don't want to do an alkyl shift, so we want to ignore that. There we go. And so we have the secondary allylic. If I did a hydride shift, that would just make it secondary and it would no longer be allylic, so we'll get rid of that. So this is good. But now, what if the resonance went to here? Let me move that down there. Now you've got here, again, this one is secondary allylic. So we're going to look at the double bonds. This one is tri-substituted, while the other one is also tri-substituted. So there's no difference between these. And so the bromine would attack either there or there to give the two possible products. But the question is, are they the same or are they different? Give me a second while I fix the structures here. I think you can see that it doesn't matter, they're the same thing. All right, this blue hydrogen, and these should have been blue, my bad. The bromine, whatever. Yeah, they're different relative to the hydrogen, but overall the structure is the same. If we were to call this carbon 1 and 2 and 3, this would be 1, 2, and 3, numbering purposes. And so you still have a methyl group at 2, you still have a bromine at 3, and let's go to 4, 5, and 6. You still have 4, 5, and 6. Right here has a CH2, that has a CH2, everything else is the same. Those are the same molecule. So we have that as a possibility. Now if we go over here to the other possible molecule, that one's secondary and not allylic, you'd have a hydride shift. For sure that would work. Moving the hydrogen there. And the positive charge here, that'll be secondary allylic, and you have tri-substituted. Again, if we did that, what you'll notice is that these are the same. So it's not giving us anything different there. So we just get one possible product. When you look at it compared to these, we have 3 different molecules. All right, and this one is tri-substituted. Whereas the other ones were di and tri-substituted. I'll point out that the numbering of this would be 1, 2, and 3 like that, and 1, 2, and 3 like this. Actually, now I'm looking at these are the same. So you'd get a mixture of the two products. All right, so yeah. And that's with one equivalent. If you added a second equivalent, then you got to think about what's going on with the remaining double bonds. But this is just adding one equivalent. All right, predict the product or products of the following reaction and propose a mechanism that explains the formation of each product. So in the first one, we've got 1,3-pentadiene and HCl in this case. So again, we could have HCl being attacked there or there. So if it's attacked on the left, you could have that secondary allylic carbocation, or you could have the primary non-resonance stabilized carbocation, which would just then undergo a hydride shift up to there. So that makes no difference. We just get one possibility if the double bond on the left goes. But then this one through resonance can give you that. I'm going to number these 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So you see, those are actually the same. So you really, again, only get one possible carbocation. If it was on the double bond on the right to start with, then you would have the carbocation here, oops, versus here. And if it was here, you would have a hydrogen shift, creating the one at the bottom. So you really only get the one at the bottom. If something's messed up, so I gotta make a copy and move that up. There we go. All right. So those are the two different possible carbocations that can form. And then the chlorine would come in and attack either of those two positions. And you'll see that this has a mono-substituted double bond, whereas this is di-substituted double bond. All right, and so what you're getting there is and my eraser won't let me erase. Sometimes that happens. Let's see. Nope. Why? I don't know. Okay, weird. So the products, you can see I was messing with things, trying to get this thing to go. The two products we would see would be that and this for the first reaction. For the second reaction, you would have the possible cations here. In there for the first double bond being adding the hydrogen to it. We have a tertiary versus a secondary allylic, and the secondary allylic is going to win. I'll remind you of Cerio, the hybridization of the atoms, I for induction. This is like secondary versus tertiary. You don't have to worry about the O, but R is resonance, and this one has resonance. And so the secondary allylic is more stable than the tertiary non-allylic. And now we have tertiary allylic. So this one is the best of all of those. And so the bromine will attack there. Theoretically, it could also attack here. And it could also, I guess, attack there, but very much unlikely. So the two major products will be those two. And this will be the major, this will be the minor. You know what, I'll add the other one on there because I'm just thinking of the kinetic control versus thermodynamic. The other one was at the end, and yeah, it was right here. There. Now I fix the structures. All right, and for these, think, so between these two, you would form that one. Kinetically, it's more stable. Thermodynamically, it's more stable, I should say. Kinetically, it should also be formed more quickly. So you'd form that one. So you actually, now that I'm thinking about it in more detail, it's going to be just the two. Whereas this would be the kinetic, because it forms first because there's no rearrangement or anything, and then this would be the thermodynamic product. For the last reaction, we have this, all right, and you add HBr to that. This molecule is symmetrical. Well, it's sort of symmetrical, I guess. We could have, let me make the requisite copies here. All right. We could have the positive charge here or the positive charge there. We could have the positive charge here or the positive charge there. This is tertiary allylic. This is secondary. This is secondary. This is secondary allylic down there. Here we have a di-substituted double bond and a di-substituted double bond versus a tri-substituted double bond and a tri-substituted double bond. The best one of all is this, because it's allylic actually, and has the tri-substituted. Actually, the other one's tri-substituted, or sorry, it's tertiary and allylic. Those are the two better ones, I should say. If we did resonance, that could go over there. And now you've got tri-substituted double bond, but it's secondary allylic. So the bromide could attack there or there. Which again, now we've got tri versus di-substituted double bonds. It could also theoretically add to there. This one's di-substituted for the double bond. Now between those, in reality, you're not going to form this because it's secondary versus you have a secondary allylic and a tertiary allylic as other options. So that is not going to form. And this would be your kinetic, and this would be your thermodynamic products there for that side. For the other side, you have secondary versus secondary allylic. That's not going to matter. We have resonance here. Giving us this secondary allylic again. And we went from tri-substituted to tri-substituted. So there's not any stability difference, but the bromine could add here, or it could add there. We do get two different products though. Sorry for my cruddy drawings. Oops. I did this one wrong. Again, this one is tri-substituted. This one is tri-substituted. And that's not a double bond. There we go. Now, as far as those are concerned, this would be the kinetic, and then you'd have both of them being thermodynamic. You have four possible products, and I'm not sure there's a good way to distinguish which one would be major, which one would be minor. Certainly that one would be the most minor. This one wouldn't be made. But as far as the other three, you're starting with a tertiary allylic, so maybe this is the major. If you're doing thermodynamic control. Actually, yeah, and so I should have major thermo, and I think this would be the major kinetic now that I'm thinking about it again, and that's because it does have the tertiary allylic making that, whereas these started off only as secondary allylic. Either way, it's a mess. An addition of bromine across 1,3-butadiene or buta-1,3-diene is going to give us the same kind of things of 1,2 and 1,4 addition. Instead of using HBr or HCl, it's just Br2. So you see the 1,2 adduct has them at 1 and 2. Now that's not the right numbering. This is technically numbered 1, 2, 3, and 4, but they're at positions that are next to each other. And then 1, 2, 3, 4 is also the possibility. Here we talk about the thermodynamic control versus kinetic control. And again, you see at 0 degrees Celsius, we're going to call that kinetic. At 40, this is going to be the thermodynamic control. And we get the 1,4 adduct under thermodynamic conditions. And the reason we can say that is that this is the disubstituted alkene, and this is the monosubstituted alkene. So under kinetic control, the most stable carbocation matters the most, and that would be the one that would be secondary allylic, versus the 1,4 adduct comes from a primary allylic carbocation, so it's less stable. But if you allow high temperatures and equilibria to form, you'll get more of this product, because the product is neutral. It's not a carbocation you have to worry about, and it has a more stable alkene. All right, we see the energy diagram for this type of a reaction here between the 1,2 product or adduct and the 1,4 product or adduct. You can see that the proton transfer is essentially the same. We have the initial formation of the secondary allylic carbocation. Then the nucleophile attacks, and the way they're going to show it would be that if it's the 1,4 adduct, it would cause that. So it's going to go over a higher activation energy up there, but ultimately the product is more stable, hence why that is over here is lower in energy than the 1,2 adduct. You know, I guess I should clarify that, again, the formation of the 1,4 adduct, I had the mechanism they showed there, but for the 1,2, the activation energy is smaller because it just directly attacks. You don't have to move over and form that less stable primary allylic transition state. Proximity effects and control of addition. All right, so in buta-1,3-diene reacting with HBr, the bromide that is kicked off is going to be right next to the secondary allylic carbocation that we see right here. And so under kinetic conditions, cold conditions, because the bromide is already right there, the attack will happen, much more quickly than if you wait for resonance to make this resonance form for the bromide to attack way over there. Or since maybe resonance isn't really happening, maybe instead the bromide just has to move all the way over here just to be able to attack that position to move the electrons over to create the 1,4 adduct. So that's basically it for chapter 21 in your book. Technically, if you look through it, you'll see that there's alpha-beta unsaturated carbonyl nucleophilic addition reactions. We already discussed those in the enolates chapter, so there's no need for me to add them here. You can look back at that if you want. But that's essentially it for chapter 21, and therefore this lecture.